Hi everyone, this is example 19 on unsteady flow, and this will be the last example for this topic. A reservoir with vertical sides is 20 meters by 20 meters in plan. On one side of this reservoir are a V-notch weir and an orifice. The V-notch weir is cut at the upper edge of this side with an apex angle of 75 degrees and its apex 0.9 meter below the top horizontal edge of the reservoir. The orifice is 200 mm in diameter with its center 1.8 meters below the top horizontal edge of the reservoir. Assuming coefficient of discharge is 0.63 for the weir and 0.6 for the orifice, and that the reservoir is full at the start, determine the following: the time it takes to discharge 240 cubic meters through the weir only, the time it takes to discharge 200 cubic meters through the orifice only, the time to discharge 300 cubic meters when both the weir and the orifice are open, and the time it takes to discharge 500 cubic meters when both the weir and the orifice are open. So for the first part, let's draw the figure to analyze the situation. So this is the weir. Just imagine, anyway, the figure is wrong. It should be here, but it's the same. So as long as this is 0.9 meter, this is delta H in general, and the head over the weir is H. Over the orifice, the head is initially 1.8, and the final head will depend on the value of delta H also. So area S therefore is 20 by 20 or 400 square meters. That's the situation now. So let's now answer the first question. The time it takes to discharge 240 cubic meters through the weir only. So this is the weir with coefficient of discharge 0.63. So the general formula for time it takes to lower the surface from initial to final is integral of area S dH over discharge formula for the weir, which is 8 over 15 C square root of 2G tangent of theta over 2 head to the 5 halves. So this is for the weir. Then let's substitute values. So by the way, the required discharge is 240, and we equate it to, this is volume, so we equate it to area S times delta H. So delta H is equal to 0.6 meters, so that's less than 0.9. Therefore, if delta H is 0.6, 0.9 minus 0.6 is 0.3. So the final head is 0.3. Time is integral of HF to HI of 400 dH over 8 over 15 times 0.63 square root of 19.62 tangent of 75 degrees over 2 head to the 5 halves. So computing for the constants, and remember the integral of h to the negative 5 half dH is negative 2/3 h to the negative 3 halves. So this is the constant 350.26, then the integral negative 2/3 h to the negative 3 halves. And by experience, it's the same as negative 2/3 1 over h to the 1.5. So 1 over initial head 0.9 to the 1.5 minus 1 over final head 0.3 to the 1.5. Or you may recall the preceding examples, example 18, and any other example involving V-notch weir. So time is 1148 seconds. And for the second part, the time it takes to discharge 200 cubic meters through the orifice only. Formula for the orifice is 2H, 2 area S quantity square root of HI minus square root of HF all over kautog, or C area O square root of 2G. So 2 area S quantity square root of HI minus square root of HF over C area O square root of 2G. Remember that HI for the orifice is not 0.9 but rather 1.8, while HF will depend on delta H also. So 200 is 400 delta H, so delta H is 0.5 meter. So therefore, initial head for the orifice is 1.8, final head is 1.8 minus 0.5, so 1.3. Substitute into the formula 2 times 400 quantity square root of 1.8 minus square root of 1.3 over 0.6 pi 0.1 square. Radius of orifice is 100 mm because the diameter is 200 mm. Square root of 19.62. Again, 1.3 is 1.8 minus delta H 0.5. So that's why final head is 1.3 for the orifice. So time is equal to 1930 seconds. For the third question, the time to discharge 300 cubic meters when both the weir and the orifice are open. So both of them are open this time. And for the fourth, 500 cubic meters when both the weir and the orifice are open. So for this slide, that's the part. So for third question, when both the weir and the orifice are opened, determine the time it takes to discharge 300 cubic meters of water. So this is now the head over the weir. The head over the orifice will be 0.9 because this is also 0.9, H plus 0.9 for the orifice. So T is integral from HF to HI of area SDH. Then there are two outlets. This is for the weir, discharge over the weir, plus discharge through the orifice C area O. C of orifice area O, square root of 2G. Then the head over the orifice is in general H plus 0.9. If H is still above the apex of the V-notch weir. So let's compute for delta H. 300 equals area S 400 times delta H. So delta H is 0.75 meter. Therefore, the final head, initial head is 0.9 for both the, in general 0.9 because for the weir it is H plus 0.9 and the final head is 0.9 minus 0.75, so 0.15. So in these limits we have 0.15 to 0.9. Substitute, so 0.15 to 0.9 for our DH 8 over 15.63 square root 19.62 tangent of 75 degrees over 2 head to the 5 halves plus 0.6 pi 0.1 square root of 19.62 times H plus 0.9. So to simplify, let's simplify these constants here. Time equals integral from 0.15 to 0.9 of 400 dH over 1.142 h to the 5 halves. Then for the orifice, including square root of 19.62 is 0.08349 square root of h plus 0.9. So this integral is by basic approach. Basic integration is difficult to do. So supposedly this is done by approximate integral by establishing deltas maybe 0.05 each, but it will take time if you do that. It's impractical solution. So if you have a high-tech calculator, then the integral can be evaluated in a short time. So I use FX991 ES plus in evaluating this integral. So the result is 1206 seconds. And for the last, the time to discharge 500 cubic meters when both the weir and the orifice are open. So we use the same formula. So HF to 0.9 for DH over 1.142 head to the 5 halves plus 0.08339 square root of H plus 0.9. So 500 equals 400 delta H, so delta H is 1.25 meters. However, 1.25 is greater than 0.9, so meaning to say the final level will be here. And based on the figure, at that time when the head is 0.9, the weir no longer operates. There's no more discharge over the weir. So the analysis would be, we'll first determine the time it takes for the water surface to drop up to the vertex or apex of the weir, because in this situation both the weir and the orifice are operating or open. When the head drops to the apex, then it's only the orifice that is open and flowing. So therefore, we should evaluate two times. One is when the water surface drops up to the apex, and the second time is when the surface drops from this apex, then 0.35, because 0.9 plus 0.35 is 1.25. So meaning to say at that time only the orifice is open, and the formula is 2 area S quantity square root of HF minus HI rather minus square root of HF over K out of. So we use this formula, and the limits would be from when the water surface drops to the apex level, H would be 0, so final head would be 0 in this equation. And we use the high-tech calculator again to evaluate that. So that's why the limits would be 0 to 0.9. So T1 is equal to 1912 seconds. For the second part, from this level at the apex, then we extend 0.35, so that 0.9 plus 0.35 is 1.25. So, and only the orifice is opened. So formula for that is 2 area S quantity square root of HI minus square root of HF over coefficient of discharge of orifice, area of orifice square root of 2G. That's the formula, right? While for HI is 0.9, because remember only the orifice is opened, so its initial head would be 0.9, its final head is 0.9 minus 0.35. 0.9 minus 0.35, where 0.35 is 0.9 plus 0.35 is 1.25. So 0.9 minus 0.35 is 0.55. So this should be 0.55, the final head over the orifice. So T2 is 2 times 400, quantity square root of 0.9 minus square root of 0.55 over 0.65, 0.1 square root of 19.62. So T2 is 1984 seconds. So the time to discharge 500 cubic meters is 1912 plus 1984. So that time, total time is 3,896 seconds. So I hope that you understand the explanations and especially the equation here. Again, it is impractical to apply approximate integral. In this case, it will take time. So I just used the high-tech calculator, and I hope that it will improve your analysis in solving problems like this.